Take a look at this. On the left, you've got a perfectly normal photo. But on the right, well, that's how a computer with a depth sensor actually sees the world. It's not about light or color. It's a map of pure distance. Now, this works great for a static scene, but what happens when the world won't hold still? How do you teach a machine to see when those sloths start moving? And that's exactly the challenge we're going to tackle today. We're diving into a groundbreaking technology called 4D TAM. It's a brand new way to teach machines how to map a world that is, just like ours, always in motion. So here's our game plan. First, we'll talk about why a world in motion is such a huge headache for computers. Then we'll get into the weeds of the 4D mapping challenge itself, before we introduce the star of our show, 4D TAM. We'll pop the hood, see how it works, and then, the fun part, we'll put it to the test and look at some frankly incredible results. Finally, we'll gaze into the future this kind of tech is building.
All right, so let's set the stage. The really basic problem here is that our world just doesn't sit still for a portrait.
The researchers behind this paper put it perfectly. For you and me, this is just life, right? It's normal. But for a robot that's trying to navigate your living room, or for an AR headset trying to pin a digital dinosaur on your floor, all of this constant change is a massive, massive technical problem. And this brings us right to the heart of it, the 4D mapping challenge. How in the world do you build a stable, reliable map of a place that just refuses to hold a pose?
And let's be clear, computers are already fantastic at this, as long as everything is perfectly still. Using a technique called SLAM, they can build these unbelievably detailed and accurate 3D models. Just look at this one. It's perfect.
But the moment you introduce even a little bit of motion, the entire system just breaks down. You get this, a chaotic, blurry, distorted mess. The computer gets confused, it can't tell if the camera's moving or if the world itself is changing, and the map just completely falls apart. This right here is the exact problem 4D TAM was built to fix. So the problem fundamentally changes, you see. It's not a 3D mapping challenge anymore. It becomes a 4D SLAM problem. And that fourth dimension, it's just time. The goal now is to do two impossible things at once. Track where the camera is, while also building a map that understands how the scene itself is bending and deforming from one moment to the next. And this is where our new tech comes into play. So let's meet 4D TAM, a completely new way of looking at this four-dimensional puzzle. At its core, 4D TAM, which stands for 4D tracking and mapping, is the first system of its kind. It uses this really powerful technique called differentiable rendering. Okay, think of it like this. It lets the system not just spit out an image, but understand how tiny changes to its 3D model will change the final 2D picture. This means it can kind of learn its way to a perfect match, figuring out the camera's location and the shape of all the moving stuff at the same time. It's brilliant. And this approach leads to a few huge breakthroughs. First, it solves for everything at once: camera position, the shape of things, their color, and how they're moving. Second, it doesn't see surfaces as a collection of rigid points. It uses these flexible, almost stretchable disks called 2D Gaussians. Third, it uses a neural network to actually learn the rules of the motion in a scene. And maybe the most incredible part, it does all of this with just a single off-the-shelf depth camera in real time. So how on earth does it actually pull this off? Well, let's break it down. It really comes down to two secret ingredients that make 4D TAM so powerful. Okay, ingredient number one is how it represents surfaces. The old way used these 3D Gaussian splats. You can think of them as fuzzy 3D cotton balls floating in space. It's kind of clunky. 4D TAM uses something totally new: 2D surface Gaussians. Think of these less like cotton balls and more like tiny, stretchable, almost paint-like discs that lie perfectly flat on a surface and know which way they're facing. This makes them way better at capturing all those fine geometric details. And the second secret ingredient, this is where the magic really happens, is something called the warp field. It's a small, efficient neural network that basically learns a motion recipe for the entire scene. You give it a point in space and a moment in time, and it tells you exactly how that point should have moved, bent, or warped. It's amazing. So here's how those two ingredients cook together. First, 4D TAM builds a default 3D model of the scene using those flexible surface disks we talked about. Then, the neural network, the warp field, watches the motion and learns that motion recipe. After that, it's actually pretty simple. It can take that default model and just apply the recipe to warp it into the correct shape for any moment in time. And the result is a perfect, moving digital snapshot of the scene. Okay, so that's the theory. It sounds great on paper, but does it actually work in the real world?
Well, let's take a look at the results, because seeing is believing.
Just look at this. On the left, we've got a rope being twisted and tangled up. This is a classic example of complex, unpredictable motion that would break older systems. And on the right, that's 4D TAM's digital reconstruction. It is not a blurry mess. It's a clean, sharp, accurate 3D model that's capturing every single twist and turn as it happens. And it works for objects just moving through space too. Here, you've got a hand moving a book. 4D TAM doesn't just reconstruct the hand in the book, it perfectly tracks their path through both space and time, which keeps the entire model crisp and stable. No blur, no ghosts. Now this one's really cool. It can even handle articulated motion. Watch as the hood, the trunk, and the doors of this little toy car open and close. 4D TAM reconstructs all of these independent movements flawlessly. It actually understands that different parts of the same object are moving in different ways. And if the visuals don't convince you, the hard numbers are just as impressive. Look at this comparison to a previous state-of-the-art method. For trajectory error, which is basically how well it tracks the camera's position, 4D TAM is over 10 times more accurate. And for appearance, where a higher number is better, the difference is just night and day. We're not talking about a small incremental improvement here. This is a massive leap forward. So, okay, the technology is obviously incredibly impressive, but let's zoom out for a second. What's the big picture here? Why does teaching a computer to see a moving world actually matter? Well, the applications are pretty much enormous. For robotics, this is a game changer. It means robots that can finally understand and work in our messy, unpredictable world, safely moving around and interacting with people. For augmented reality, it means AR glasses where digital stuff can be perfectly anchored to real, moving, changing objects. And it unlocks this wild potential for live digital twins, creating perfect, real-time virtual copies of dynamic systems, anything from a chaotic factory floor to a beating human heart for a surgeon to practice on. Honestly, this is just the beginning. The real question isn't just about what 4D TAM can do today, but what we're all going to do with it tomorrow. When our machines can finally see the world the way we do, not as a static photo, but as a living, breathing, constantly moving reality, what new tools, what new experiences, what new discoveries are we going to build?